continuing on from last time, we were talking about process and code migration. It's a new topic we started after finishing virtualization. So as I was mentioning, this new chapter in the book, it refers to code or processes moving from one machine to another. Realize that this is a component of distributed scheduling, because when we were talking earlier about scheduling jobs and moving them from one machine to another, I mentioned that you can do it before the process starts, move the code and just start it there, or you can move it after the process started. If you do it after, it's called process migration. If you do it before, it's code migration. So these components are essentially part of this distributed scheduling framework. Of course, they can be used for other things as well, but they are used in the context of balancing load or moving jobs within a cluster and so on. So I mentioned code migration and process migration. So the thing to realize is when you do code migration, typically you migrate the code and you start a process. And in most cases, the process will execute in a separate, the code would execute in a separate process, an independent process is started up. Occasionally, the code may actually execute in the process that triggered the migration. An example is Java applets running in a browser. A browser downloads a Java applet, executes it, but that execution is typically in the context of the browser process. The browser process is the one executing the code. Okay? So that's code migration. Process migration, the way it typically works, there are two methods. I mean, they are sort of similar. One is called remote cloning. Okay? Cloning is essentially mirroring. So what happens in remote cloning is you pause the process, okay? You clone it, you make an exact copy of that process on another machine, okay? And you resume it there and terminate the first copy. Okay? This is referred to as cloning or mirroring of the process. Okay? The other one is basically you migrate the process, which is you may copy its state, you can copy it to disk and then load it somewhere else, or you can do just copying of the memory pages and so on. Okay, they are sort of the same in what they are trying to achieve, but these are the two techniques that are available. So this slide shows all the combinations of the various dimensions that you have to worry about, okay, when you talk about either process or code migration. So we'll broadly refer to that as mobility. You have weak mobility, that's a term that's synonymous with code migration, or you have strong mobility, okay, which is process migration. Within each, you can be sender initiated or receiver initiated. Whether the sender triggered the migration or the receiver triggered the migration. Okay, there are two entities when you're migrating. The sender, which is where the code or the process was executing or was triggered, and the receiver. So depending on who started the process, your sender or receiver. Okay. That ties neatly into distributed scheduling, where I said you can be receiver initiated or sender initiated, where you go looking for jobs or you go trying to send some job. Okay, so that's the other dimension. The third dimension is where the migrated code executes. Okay, you can execute, or how it migrates. Okay, so you can migrate and execute it in the process. You can migrate and execute it in the target process or in the process that initiated it. Okay, so these are sort of the two dimensions. Now, as you can imagine, you can do strong or weak sender or receiver. You can do execute in a new process or migrated in the initiating process. So you get these various combinations, and depending on which of these you pick for your system, you will get a different point solution in the whole space, okay, of mobility. Okay, that's sort of an overview of, or a slide that shows an overview of the various combinations. Okay. Now we'll talk about the more interesting problem here, which is what happens to resources. Okay, so the big problem in process or code migration is not the copying of the process state or the code. Okay, that is easy to do. The problem is what happens to resources that this process was trying to access. Okay, so suppose you have process A on machine 1. Okay. It has a file open. Okay, it's a file on a local disk. Okay. You migrate the process to a second machine, and the process is just going to continue execution. Typically, the process doesn't actually know it has moved. Okay, this is transparent to the process. The OS is not going to tell the process you move. The process doesn't know or care. It's a traditional process. So when the process executes on the second machine, it still expects to have that file open because the file was open and it was reading and writing to it. Okay? But the file doesn't actually exist on the second machine. Okay? So that's a problem. How do you deal with it? Yes, and you can have more complicated versions of this problem. You may have network sockets open. Okay? The socket is tied typically to an IP address on the machine where the socket connection was open. You just migrate the process to a different machine. Now it's executing on a machine with a different IP address. Okay? The socket connection will typically break in this case. Okay, so and the process will not know what happened because the socket was open, it was transmitting or receiving data successfully, and now things stop. So you need to make this, to make process migration transparent, you need to deal with resources. Okay, whether the resource is a file, it's a piece of hardware that you are accessing locally, or it's an abstract resource such as a socket. Okay, so how do you deal with that is the problem. Okay, so there are three different techniques to deal with this. Okay, but let's think of some ideas first. What would we do if we wanted to make this transparent? Okay, the process you moved, what happens to the resources the process is accessing?
As for some kind of resources, you can move them as well.
Okay, some resources could move with the process. Okay, you could think of a file. Okay, if you move the process, why not move the file over? Also copy the file and keep it local in this, let's say, a similar directory, so it can continue to access it. Okay, so moving a resource with the process is a potential mechanism. Okay. It works if the cost of moving the resource is low. If it was a 10 kilobyte file, it's okay to move. If it's a 10 gigabyte file, like a database, it may be expensive to move. Okay, so it's certainly possible to move, but it may or may not be cheap to move. And that's one approach. What other approaches can you think of? Yeah.
You could have some like middleware approach where you don't let the process actually touch real resources in the first place.
Okay, and then what happens after you move it? You
Go middleware figures it.
so you let somebody else deal with the problem. That's a good approach. Always let somebody else worry about it. It's not a bad approach actually. We will look at middleware that makes some of the migration transparent, although I'm not going to talk about that here in particular as to how that happens. But yes, you could essentially just have something else figure out how to give access to a resource. Okay. Any other thoughts, ideas?
And of course, you can also do nothing. Just assume that the resources will still be available at the other point.
Okay, so you do nothing, which is you're not really doing nothing, but you are assuming that you can still access the resource from the other machine. Okay. You provide remote access to the resource. Okay, so resource may not move, the file may still stay on the machine, but if there's a way to access that file over the network, problem solved. Right? You still get access to it, it's just that now request traverse over a network in order to get access to it. Think of a printer as an example. Okay? There's a printer connected to the machine, your application is designed to, let's say, print something. Okay? So you could print locally to your local printer, but if the process moved, you could send the job over the network, and essentially the printer is acting like a network printer. You just print over the network. Same thing with files. If you have a network file system, you can access that file over a network file system. The file doesn't have to move, for instance. Okay. So you have talked about a set of techniques. Let me go through them in a more formal way. Okay. So to answer the question of how the resource can be accessed by this migrated process, you have to first understand what type of resource is it. Okay, so there are three types of resources that we'll talk about. The resources that you bind by identifier, bind by value, bind by type. So what does binding mean? Binding essentially means when you try to access a resource, you provide a name for the resource. So it's a printer, or it's a file name, and so on. Okay, that name attaches the process to a particular resource. Okay, and the binding may depend on what kind of resource it is. Okay, so when you say you bind by identifier, you say that the resource has a name and you only want the resource with that name and nothing else. If you say I want to open file project1.java, you only want project1.java, you don't want project2.java even though the name sounds similar. Okay, so that doesn't make sense in that case. So in this case it's a hard binding. The resource identifies a unique, the name identifies a unique object, and that's the object you care about. Okay? Nothing else. Web pages, URLs are an example also. A URL specifies the name of a web page. If you type that name, you expect that page to show up. You don't want something else. Okay? But there are, so in other words, you cannot substitute a different resource for this resource. The name has a unique mapping. Okay? But you may have resources that are bound by value. Okay? So when the process starts up, it needs, let's say, the JVM. Okay? That JVM is a resource that the process needs to execute. Okay? And you may have a version, let's say JVM version 2.x. Now, so long as you have JVM version 2.x installed, you don't want that particular file alone. If you move that process to another machine, if JVM 2.x is installed there, then you are willing to use that version there. Okay? So this is a somewhat looser binding. In the first case, if you open the file project1.java, that's the file you care about. Even if there was another file called project1.java, a different file on a different machine, that's not the file you want. Okay? So you want this file and this file alone. But in the second case where you have by value, you have a looser binding. The name identifies a resource, but you can substitute another resource with the same name, so long as the names make sense. I mean, if it's a JVM, for instance, or GNU C library or the math library, you are okay with it. So long as it's the right version, you know it's the same thing. Okay? You are willing to do a substitution. Okay? So, and the last one is the loosest binding of all, which is saying that you are going to bind by type. You want to print. Okay? On this machine, you may have access to a HP printer. On another machine, you may have access to a Canon printer. Both of them will print your job for you. Okay? So long as you get a printed copy, you may not particularly care about whether it's printing on an HP printer or. So you can even have, you only have a class of a resource. Even the name may be different. You are not going to insist that I have to print on the same HP model 3020 even on that machine. Doesn't matter. Okay, much looser binding. Okay. So what this simple example should tell you is whether how you deal with resources when you migrate a process. It depends on the type of the resource. In certain case, okay, the resource you care about is unique. You cannot substitute it. So either you have to move it with the process or you have to provide remote access. Those are the only two mechanisms. You can't substitute it with another resource of the same name. Okay? You can't say there's another file project1.java, so I'm going to let you access that on that machine. Different file, different content. Doesn't work. Okay? In the second case, so long as the resource has the same name on another machine, you are willing to take it. Okay? Like a JVM version, some version. Okay? So you know that it's the same thing, so you are willing to use that library, for instance. Okay? And the third case is much looser binding. You just need a class of a resource. You don't even particularly care about is it the same model or the same name. So long as a resource within the class, you can substitute it for a local resource that this process was executed. Okay? So what this also should tell you is when you migrate a process, what you do as far as resources are concerned will depend very much on the type. In some cases, you have to move it or provide access. In other cases, you can replace it with some resource of the same name or some resource of the same class, not even the same thing. Okay? So this is basically going to tell you how you deal with it. Okay? There is another dimension to think about, which is what kind of a resource is it in terms of whether its ability to migrate or not. Okay? There are some resources that we will call are unattached resources. These resources you can move. Okay? A file may be an unattached resource. The file can hop from a machine to machine, for instance. Okay? Other resources are what we will call fastened resources. These resources can be moved but at a high cost. A large database being an example. The cost of moving it is very high. You can move websites, entire website. But the cost is high because things have to be reconfigured for those web pages to become accessible with the same name. Okay, there's a website may have a name, www.foo.com. Okay, so just moving something over doesn't make it accessible from a different machine. So more work has to go in order to make those resources available. The last one type of resource called fixed resource. These are resources that are attached and cannot be moved, no matter what the cost. Okay? Hardware device attached to a machine is an example of a fixed resource. Okay? You cannot actually move. You can physically detach a printer and move it, but it's not going to go over a network like data does. Right? So typically these kinds of resources don't move. Socket endpoints are another example. They are tied to the IP address of that machine. You can't just move that socket endpoint because it doesn't work. The other machine has a different IP address. Okay? So you can have unattached resources, fastened resources, fixed resources. And you may have resources that are attached or bound to by identifier, value, type. Yeah, so here is a table. It looks more complicated than it actually is, which says depending on what the binding is, identifier, value or type, and the cost of moving it, whether it's unattached, whether it's expensive and it's fixed, you may have to use different strategies. Okay? There are actually only three different strategies. Actually. One is what's called global reference. Global reference essentially means that you can access this resource remotely. You have a name, you can access it over a network. Okay. And then you have another technique which is move or copy, which means you can move or copy that resource from one node to another. The third one says rebind, which is substitute with another suitable resource. Okay. So your strategies that you have are you provide access to the resource over a network, you move or copy it, or you substitute that resource with another resource. Okay. So when you migrate a process, you have to look at all the resources it accesses. You have to find out where in this quadrant, it's not a quadrant, where in this sort of grid it falls in terms of how it's bound and the cost, and you have to pick one of these strategies, saying this is what I'm going to do to handle this resource, access to this resource. Okay. And there are many possibilities for some of these items, and we'll see. You pick the one that makes most sense. Okay, so, for instance, if you have a resource that you access by identifier and it's unattached, okay, a file is an example, you have the option of moving it, okay, you move the file. You also have the option of providing remote access to the file. If you don't want to move it even if the file is small, so if it's accessible over a network, move the process, leave the file there, send a request to that file over a network and let it read or write over a network. Okay. So both of these options are available. So you can do move or do global reference. Okay. If you have anything by type, okay, these are loose bindings. Okay. This is where I said you can essentially have a printer, okay, and you don't particularly care about the model of it. You may care whether it's color printer or black and white. At that level you may care, but so long as it has the right characteristic, the vendor may not matter to you. So it's easier to substitute. So in this case, in this row, you will see that rebind is always the preferred option. You can do other things as well, but substitution is the best choice. If you have another resource of that type available, substitute and be done. Don't worry about moving it or providing remote access. Of course, you could provide remote access as well. As you will see, global reference is always a choice. Okay, global reference is send the job over a network and print it to the original printer. Okay, that is always an option, but substitution is a cheaper option. Okay, just substitute it if there is another resource available. So this row is always going to say global reference. Okay. For identifier, okay, again when you have files for instance, when it's cheap or unattached you move, and when it's expensive to move or fixed you do global reference. There's no choice. If you cannot move it, move that resource, or it's very expensive to move, you only have to allow that resource to be accessed over a network. Okay, so, which is basically what we say, establish a system-wide reference, which is you access it over a network. Okay, so GR is a popular choice when it's expensive or when it's fixed, you cannot move it. Okay. As you will see, there will be some other choices as well that pop up, but those are the most suitable ones. Okay. So the thing to take away is when you are designing a process migration system, You have to decide how do you deal with resources. Are there some constraints? Yeah, how for different kinds of resources, how will you continue to provide access if the process is actually going to move? Okay. Now, I didn't particularly talk about the most thorny resource tends to be network sockets, because it's now you cannot move it. Okay, and even saying provides a global reference is not what does that even mean, right? So you have. So let's say there's process A that's running here, it is attached to a socket, and there is data coming and going out. Maybe there's another process B that's accessing it over a network. Okay? And you essentially move process A here. Okay? This has IP address 1, this has IP address 2. Okay? And the B doesn't know that process A has moved. B will basically has an open socket connection to this machine. Okay? Because sockets are tied to IP addresses. Okay? So when the process moves, basically the socket is meaningless for this process. Okay? So how do you deal with this problem? Okay, so what would you do?
You can forward the data which is coming on this machine.
Okay, so you can forward data. Okay, now that's true, and I'll show you how, but where does this fall in the spectrum? Somebody said rebind. Okay. If you rebound, then basically that would mean that you substitute this socket with this local socket that is bound to that address. Okay, so that would mean that's a new socket. Okay. So just doing rebind doesn't help us because this process is still sending packets here. Okay, what we decided we would do is this copy is gone. We'll keep this socket alive, okay, and we'll make a local socket which is essentially a dummy socket there. Okay, and we are just going to, whenever packets come here, we create forward. So this is essentially a tunnel that you set up. You are tunneling packet. So as far as this process is concerned, it just still thinks that the original process is sitting on the original machine. This socket is still alive. All that you are doing is whenever a packet comes here, you simply forward it to its destination. Okay, this is exactly what you do with the post office when you move. Okay, you can leave a forwarding address. Okay, that way anybody who sent you mail, snail mail, will actually doesn't have to know your mode, the mail gets delivered to you. Same thing has to be done here. Okay, that's forwarding. But it's not moving or copying for sure. It's not rebinding. What you've essentially done is established a global reference, but it's a funny way to do it. Okay? So you're sort of creating a tunnel to keep it transparent. Okay, so all the reverse is also true when the A sends packets back to B, they have to flow through this socket so that the original IP address is retained. Any questions on this? Okay, so those are some issues you have to worry about when you do process migration, how to deal with resources. And there are many choices, and depending on the binding and the cost, you have to pick one. Network sockets tend to be the hardest to keep the thing transparent. The other choice, of course, you have is to say, I will not deal with network sockets. So if you have a process with open sockets, do not migrate it. System cannot handle it. You can always put constraints. And you don't have to say I have the most general, most flexible migration system that can deal with anything. You can say this migration system cannot deal with processes that do network I/O. Other types of processes can be migrated, but ones that have network I/O cannot be migrated because you don't have a good way to deal with IP communication. That's the other approach. You put constraints and just don't migrate certain types of processes that access certain kinds of resources. Or you have to come up with schemes like this. These are design choice. So next problem. So until now we have implicitly assumed that the sender and the receiver machines are homogeneous machines. They run the same OS, they run the same processor, architecture is the same. So when you migrate the binary of the process, it will actually execute them, because it's the same process and so on. Okay. What happens if and the sender and the receiver are heterogeneous? Either they are slightly different variants of the same processor family. One may be newer Intel CPU has some new features and the other one is older. Okay. Or they may be completely different. Okay, one is let's say Spark and the other one is Intel. One runs Solaris or Windows, other one runs Linux. Okay. Can you move in such scenarios? Can you move processes when the underlying OS and or hardware is heterogeneous? Okay. One design choice you could say is no, I do not want to deal with all that additional complexity. Okay, well, it's too difficult. You can't just simply take code that was compiled on Spark, move it on x86 and expect it to run. Even the assembly instructions don't make any sense. Right? But suppose you wanted to do something, what could you do? Okay. This picture shows a fairly complicated process. I mean, it's looking more complicated, but what it essentially says is if you want to deal with heterogeneity, right, you have to realize that the code is not going to run, first of all, because if the binary formats are different across operating systems, and there's certainly the assembly instruction family, the language is different across hardware families. Okay? So something has to be done to deal with the code segment. Okay? At least the data segments are okay. Okay, so if you think of a process as having three parts: code segment that contains the code, stack and heap. The stack and heap are data. Okay? Data is bits. Okay? You can move the data over. You will have to deal with issues of whether the machine is big Indian or little Indian. Okay? People know what big Indian, little Indian means, right? Whether basically your most significant bit you read left to right or right to left. Okay? In some machines you read left to right, other machines you read. So if you just transfer bits and you go from a little Indian to big Indian, all the bits will be flipped. You will read the integer in the reverse way and the value will be different. So you will have to, when you transfer, flip the bits and store them the other way. Okay? But so long as you deal with that translation, okay, you can deal with the data segment. The big problem is code segment. Yeah, resources are the same issue, whether it's heterogeneous or not, you should still deal with it the same way. Okay, code segment, the way you can do is, you can actually, if you had access to the source code, you could recompile the code segment. Okay, you have to keep track of what the register values were, and then the recompiled code segment, you can actually resume execution from where the process began. Okay? So you could do that. Okay, when you transfer the process, you recompile the code segment. One possibility. Okay? Very clunky and clumsy, may not always work. Okay, because there are all these pointers and all of those things. There are addresses, so when you compile it and the data segment has already been populated, things may go wrong. But in theory, you can say that the data segment moves over, the code segment is recompiled so that it runs on the new architecture. I move it and all should be good. Okay, easier said than done, but that's a principle one could follow. Okay. The other approach is that you can do binary translation. I mentioned the other day when we were talking about application level virtualization that or even emulation, that you can do instruction by instruction translation. So I mentioned at least a couple of times this Rosetta technology on Macs, which does binary translation of PowerPC processes and let them run on Intel architecture. Every instruction is translated on the fly and substituted by corresponding Intel instruction. Okay, so you can move the same process, but then it executes under sort of control of a binary translator. If you did that, then things would be fine as well. Okay, in that case, you don't need to worry about recompiling. Just move the whole thing over. There's a translator there that is actually doing this on the fly. Okay. The first case, the compiler did the translation for you. You basically recompiled this code. Second case, you did binary translation. Okay. Of course, if you are scripting language, then this is easy. It doesn't matter. Right? So if you have Python, let's say, okay, you can actually move a Python process, and if you move the Python source code with it, it will work. Okay, because it's interpreted on the fly. So long as you have an interpreter, it should work. Whether it's a different, same platform, different platform, shouldn't matter. Okay. Same is true if you have application virtual machine. Java is another example. Okay? If your process is a Java process that runs on a JVM, the underlying process architecture platform becomes immaterial. Okay? You can take a Java process that was running in a JVM on Windows and move it, migrate it and run it on the same JVM, runs on Linux. Because the JVM provides an abstract interface that is independent of the underlying hardware interface, but this doesn't matter anymore. You've taken the heterogeneity and you're done away with it, saying it doesn't matter. Yeah, the process is actually running inside a JVM. The JVM provides the same interface regardless of whether it's running on one platform or another, or one architecture or another. Yeah, so you could just say that if this only works if you have these kinds of applications. So JVM is a good example of migration in heterogeneous system. You can actually migrate Java processes. Okay, so these are some ideas of how you deal with migration in heterogeneous environment. So the most complicated thing I mentioned, nobody does. There are some research systems that do recompiling code. The binary translation or running it in virtual machines, or just doing this for scripted languages, where you haven't compiled it to a binary, it's just scripted, it's source code, so source code should work regardless of the platform, so long as you have the interpreter. Those approaches would work fine. Okay? Questions here? Okay. So last point about migration that I want to make is on virtual machine migration. Okay. So this is actually by far the most common approach to migrate processes. Okay. So what happens in this case is that you take a virtual machine that was executing on one physical machine, and you can migrate that entire virtual machine to another machine and execute it there. All the OS, all the processes in there migrate without any problem. Okay. There are a couple of different ways to do this. Okay. You can, if you have actually used VMware or Parallels or VirtualBox, you know that you can suspend a virtual machine. Okay. What it does is it takes a running virtual machine, it suspends its memory state to disk. Okay. You can take that virtual disk image and you can simply copy it over to another machine and you can resume execution there. And it will just resume. Your OS processes, all of them will actually move over. Okay. And everything looks the same because you are still executing on a virtual machine, not on the physical hardware. Okay. The virtual machine abstraction hasn't changed. The physical machine abstraction is the one changed. Okay. But this requires you to have a downtime where you suspend it, copy and resume. So during that time the process doesn't execute. It's in suspended state. Okay. There's another technique where it allows you to do this migration live while the application is actually continuing to execute inside the virtual machine. There's no downtime at all. Okay, so this is referred to as virtual machine migration. I can show you a small picture here. Okay, so this is machine 1, let's call it machine A. This is machine B. Both of them run a hypervisor. Okay, so this is VM, this running here. Okay. So you can take this virtual machine which has an OS and it has many processes, okay, and you can simply migrate it to another machine. And today's hypervisor allow you to do this live. By live, what that means is the copying process starts while this VM is still executing. Okay. And once all the memory state has moved over, you are going to essentially switch the execution from this copy to that copy, and the machine, basically all the processes continue to execute, but now essentially you've gone from one machine to another. Okay. There's a question, yes.
Okay, so what happens in your socket example?
Yes, I'll come to sockets.
Okay.
I'm not done talking about, we'll deal with how do you deal with resources and particularly sockets in just a second. Okay. First we have to understand, yes, go for it.
I think the machine is the memory is changing.
Yes.
Due to the latency, and the B is
Yes. So
because the copy can't be done.
good point. So all points that I was about to make or ask about at least. So I said, how does live migration work? So you say, migrate this VM from here to here. Do it live while the process is executing. So what will you do? You will say that, let's say this is 1 gigabyte of RAM. Right? RAM has pages. You will say take page 1, copy it here, take page 2, copy it here, take page 3, copy it here. This is called iterative copying. So you just copy pages 1 through n. Okay? And once you're done that, a copy of each page has moved from here to here. Okay? But realize that this is happening while the process here is continuing to execute. If the process continues to execute, that means this page memory contents can continue to be modified while this copying is taking place. Okay? So although you may have moved a copy of all of these pages over, by the time you're done copying all these pages, some pages here have changed already. Some may not have, but some have changed. Okay? So now what do? You can't just resume execution there because that some data is stale there. What would you do?
Just copy all the dirty pages over, because the memory will already have, like caches or something will already have information about all the dirty pages. You can just migrate all the dirty pages over.
Okay. So there's only one choice. If the data has changed, copy it again. Okay. But hopefully in the second round of copying, the amount of copying that you have to do might be less, hopefully, because only some data would have changed. It won't be that every single page changed in the past 5 minutes. Some process is terminated, some new process is started up. So some fraction of the pages, memory contents are changed, but not all. So in the second round, you just identify. So while you are copying, you are actually tracking. You have to start tracking what pages are actually being modified. So for every page for which there is a check mark saying it was modified, in round 2 you are going to copy that again. Okay. So in round 1 you copied all the pages, some of the pages have been modified, so in round 2 you will copy maybe some fraction of that. Okay. Process is continuing to execute, so while round 2 copying is going on, some more pages will change. Okay. So you will start another round, saying okay, but hopefully because each round is copying fewer pages than the previous round, it takes shorter time, and in that shorter time even fewer pages get modified. So there is a heuristic, it's not guaranteed. Right? So the heuristic says in each round you will successively copy fewer and fewer pages because it takes shorter time to copy those pages. In that only some subset of those pages or some other pages get modified. Okay? So after a few rounds, let's say k rounds, the amount of memory that you have to transfer may become very small. Maybe it's like 100 pages out of a million pages, or not million, maybe 100,000 pages. Okay? So that is sufficiently small that what you do at that point after k rounds is you actually pause the VM, saying now is the time for me to switch this machine. Oh, so I pause it. So at this point no more memory changes can take place. Okay? Pause it, transfer the last few pages. Okay, once you are transferred, now these two are mirror copies. Everything here is identical to everything there. So at that point you just terminate this VM and this VM starts executing. Okay? So this is referred to as iterative memory copy, where you basically start in the first round you do a long process of copying all the pages, just give me gigabytes of RAM, everything has to be copied. Next time hopefully, while that was happening, some memory changes, so some subset of that has to be copied and so on. And then when you have reached a point where that delta from the previous round is sufficiently small, pause, move the last few pages, and then they are identical copies. So either of them can be resumed. They are bit by bit identical at that point. Okay, so you can say, now I resume this one and stop that. Okay, except for one detail, okay, which is the networking part. Okay, this is still a different machine. Right? So you have to deal with the network. Okay, how will we deal with it? Okay, we don't want to do all this complicated tunneling. Okay, that's too much.
If at other place the VM runs behind NAT, let's say migrated.
Okay? Do people understand what was the suggestion? Okay. First thing is you have to realize what IP addresses mean in the virtual machine world. Okay? If you remember last time what I said is, there's a physical machine here, that's a server that has an Ethernet card. This Ethernet card has an IP address. Okay. Virtual machine is an emulation of a physical machine. It emulates all of the resources. Okay. So in particular, it emulates an Ethernet card as well. So not this card, it's emulated, it's a software emulation of Ethernet card. So to the OS thinks that's the Ethernet card. Okay. So typically for the virtual machine to work, that VM has to be given an IP address that's distinct from the IP address of the physical machine. Okay. This is an Ethernet card, that's an emulated Ethernet card that has its own IP address, typically. Okay. So all processes are assuming that that's the IP address of the machine. What happens is when packets come here, the hypervisor is just mapping the packet simply onto that Ethernet. Okay. So it's just basically, so there may be another VM here. So you are simply multiplexing all of these interfaces onto this one physical interface. Okay. So this is the part that is going to basically help us in this case. Because the virtual machine has a logical Ethernet interface which has a distinct IP address from the physical machine. When you move this, the interface also moves with it. Okay. So you can essentially migrate that IP address over. This IP address is going to stay the same. The IP address here is going to basically move over. Okay. So long as you've been smart enough to ensure that there are no conflicts. You don't want to reuse that address here. So if your IP addresses are distinct across all the VMs in your entire cluster, then this you can essentially just move that IP address over. Because the Ethernet interface has moved over. That's emulation. It's emulated interface. It just moved with the virtual machine. So let the IP address move. There's no reason because it's tied to that Ethernet address. Okay. The IP address moves over. There is nothing to do. You actually made the IP address a more elastic resource. It actually moves with the OS. If you just had a process, the process was tied to the physical Ethernet address. When the process moves, the physical Ethernet card doesn't move. Because you are moving a virtual machine, not a process. Everything that, all the emulated resources on the virtual machine move. So you have the luxury of moving the IP address over. Okay. So if you move the IP address over, the processes inside the virtual machine, you don't see anything. They just see the same interface, same IP address, socket connections work just the same, etc. Okay. Okay, now there's one small detail I sort of not forgot but did not mention, which is how does, let's say, client B or whatever, some machine B that was talking to this VM know that now it has to send packets here. Okay, the IP address has moved, but something has to happen inside the network so that packets that were being routed this way start going this way. Is that clear? What the last point is, the IP address has moved, but the network needs to know that this machine is now sitting on some different server, so that packets are to be sent there, not here, at the IP address. So that is typically now to address that this is not a trivial problem if you are doing this across a wide area network. Okay? Which means it goes from one subdomain to another. Okay? But it's a much simpler problem if this is happening over a LAN. Okay? If all these machines are over a LAN, then basically it's a matter of telling an Ethernet switch, because then you say that rather than sending it there, you basically send the packets. So this you can just do by sending a simple message to the switch saying forget everything you know about this MAC address and the IP address binding and relearn it. So when this machine starts sending packets, it will now think that the machine is connected to that port of the switch, not this port of the switch. So it simply just starts forwarding packet transfer. Switches are already built to do this. Okay, you can essentially disconnect cable from one port of the switch and connect it to another port, and packets just start flowing because the switch knows that now that machine has just switched to a different port. Right? So this works at an Ethernet level just fine. At the router level, you may have to do additional things, but that we don't worry about. Okay? This is virtual machine migration. Okay? So it's much more easy, and this is all done live. So the process essentially doesn't take a downtime except for that last pause when you switch, and that pause is less than a second. So you see a minor blip and the machine just shows up on a device. They don't have their own Ethernet interface. Processes are simply opening a socket and using the interface that's connected to the physical machine. So when you move the process, it has no choice but to send packets on the new interface. Okay? The only thing that saved us here was there was a interface that was tied to the virtual machine as independent from the physical host. So you can move it with the entity you are migrating. Here it's a virtual machine. Okay, so if you do that, then you are okay. Any other questions here? Okay, so that's virtual machine migration. Very last point I will make very quickly. I spend more time here than I wanted to is case study on from code migration, which is viruses and malware. Okay, by far the most prevalent use of code migration is for malicious purposes. And examples being viruses and malware. So viruses are essentially code, typically code or even programs that hop from one machine to another. They self-propagate, okay, and then they infect another machine, typically through a security bug, and then the code starts executing on that machine. It tries to infect other machines and so on. Okay. That's an example of code migration. Okay. It is sender initiated typically, where you have proactive viruses that go and infect other machines. It could be receiver initiated. If you get, let's say, a phishing attack in email saying click this attachment and you will $1 million or some such thing, and you click that attachment and infect your machine, that's a receiver initiated example. Okay. So you have both sender and receiver initiated examples of code. The other thing I should mention is this is clearly all mobile code. The code is mobile, it can move from one machine to another, can execute on different machines and even autonomously infect new machines. Okay. So the only real use case other than virtual machine migration of code migration these days unfortunately is for malicious purposes. Okay. You can of course make better use of these technologies, but they are not that widely used yet. Okay. So with that I'm going to switch to a different section of okay, so we are done with migration issues, okay, distributed scheduling. So at this point we have actually finished a lot of material on distributed scheduling. We took a detour, looked at virtualization on the way. The reason I wanted to cover virtualization was to make the connection with virtual machine migration. Okay. So we are going to switch gears, talk a little bit about server architectures, and the reason I have these 4 slides here is because you will soon get the lab, so I just wanted to have this material covered in class before you start thinking about how to design your applications. So we are back thinking about client-server architectures. No? Okay. So we assume that your distributed system includes a client component and a server component. We are going to worry a little bit more about what the server component looks like. I've already said a few words about this when I talked about multi-tier architectures for servers. I said the server is not one entity, it could be a distributed set of processes, each having its own tier. I remember I gave the search engine example of different tiers, and I gave an example of a bookstore with a Java, HTTP tier, a Java tier, a database backend, and so. So we'll look at all of these issues in a little more detail in the next few slides. Okay. So when you design your server, okay, these are sort of design principles, as you will see. So when you design your server, you have 2 choices, whether to make the server what's called iterative or concurrent. Okay. Iterative server is essentially a single-threaded server. Okay. So essentially what it does is the server has a thread that's just listening to requests. Okay. Request 1 comes in, that thread goes off, processes that request. If additional requests come in, by when the request is being served, they get queued up. Okay. When request 1 finishes, you go back and say, is there another request waiting? If so, you pull that request, start servicing it. If not, you wait for a request to come. Okay. So you sit in a loop, this is why it's called iterative. Sit in a loop, grab a request that has come in, process it, repeat. Okay. If there's no request, you wait until the request comes, and you iteratively process. Okay. That's one very straightforward way of designing a server, which is iterative. Okay. There's no parallelism here, as you can imagine. Okay. You're processing one request at a time. Okay. The request takes a long time, it's doing some I/O, It's an iterative process, so you wait. You make other processes wait, rather, or other requests wait. Okay? Not the best way to design a server. Okay? A better way to design a server is to make it concurrent or multi-threaded. Okay? In a multi-threaded server, what happens is, whenever a request comes in, okay, you will typically, in the simplest case, spawn a new thread. Okay? You will say, request came in, start a new thread. Okay? And you hand over that request to the thread saying, here is a request, go service it. When thread goes off, it starts doing whatever it needs to do to service a request. If another request comes in while this thread is servicing the request, start a new thread. Okay? Hand that request to that thread. Okay? So at any time, you may have some number of unfinished requests in your server, each being processed by its own thread, and they are all executing concurrently or in parallel. Multi-core servers. Okay. So you can take advantage of parallelism when you design concurrent servers. Okay. So in most cases, servers will tend to be concurrent, multi-threaded, okay. And that just allows them to service a larger number of requests all at once and make better use of the resources on your server. Okay. In the context of some sophisticated servers, rather than spawning a new thread for every incoming request, you have a pre-spawned pool of threads. So you have a pool of threads. Let's say when the server starts up, you create n threads, and maybe 10 or 50. And all the threads just sit idle. Okay? And there is a master thread that's listening for requests. As each thread comes in, it hands it over to an idle thread. Okay? Here is thread I is idle, go finish this, service this request. Okay? So this is called a dispatcher or scheduling thread. So you are essentially taking incoming requests, handing it to the thread. That thread goes off, services the request, and rejoins the pool. Okay, when it's done. Okay. Now think about advantages and disadvantages of using what is called a thread per request model. So and a pre-spawned thread pool. Okay. Both are concurrent. In one case, every time a request comes in, you start a new thread. Thread goes off, services the request. Once the request is done, thread terminates. Okay. The same thing is true done for every single request. The second case, you have a pre-spawned pool. Okay. You pre-spawned a certain number of threads. Requests come in, you try to find an idle thread in the pool, and then hand the request to the idle. Okay. What are some pros and cons of this approach?
So in the first case, you can can handle virtually any number of threads concurrently, any number of requests. But it's harder to get performance guarantees.
Okay. The first case, you can handle any number of requests that come in. Because every request comes in, start a new thread.
Which can be bad in some cases if you get too many requests.
Okay, so that's good and bad. Right? So in the second case, let's say you start with n threads. So that means the concurrency in your system is n. Okay, if n requests all show up at this more or less the same time, you can handle them in parallel. Okay, more than n show up, all n pre-spawned threads are busy. The remaining ones have to wait until one of these threads becomes idle again. Okay, that's the model. You have a fixed number of what are called worker threads, and if you max them out because there are that many requests, if a new request comes in, it has to wait. Right? In this case, there is no such limit. Okay, n plus first request comes on, I spawn n plus first thread. Doesn't matter. Okay, there's no limit that you set. Okay? And as has been pointed out, this is both good and bad. Okay? It's good if basically the n plus one thread doesn't max out system resources. Okay, that you can actually, system has enough resources to actually handle one more thread. Okay? It is bad if with the n threads are already maxed out the system resources, you spawn yet another thread. This will tax your system further. It may have been better to make that request wait. So in the pre-spawned thread pool, if you choose n carefully, where n is the maximum number of threads you can sustain in the system, which are let's say 4 gigabytes of RAM, 2 gigahertz core, I said that's the hardware resources. This machine can handle 153 threads. Okay, anything more than that, system becomes saturated and performance starts going down. Okay? So if you think carefully about what hardware your server runs on and choose N carefully, this is going to be as good. Here, if once you reach N, you start spawning new requests and you will actually hurt the performance. Okay? But the advantage in this case is you don't need to know what N is. You can run that server on a different machine and it will still work. Here, if you move it to another server, which has, let's say, different amount of resources, you have to again figure out what's the right N. Okay? So that the system administrator has to figure out. Any other thoughts on pros and cons?
There is overhead of thread creation and destroying in the first one.
Okay, so overhead of thread creation, the termination, no such overhead here. Okay. So every time request comes in, create a thread, system call. You call pthread create, that's going to go and trigger a system call. If it's kernel threads, then the kernel has to allocate resources. When you are done, you say pthread destroy. Okay. Again, system call, again the system has to, OS has to go and deallocate resources. That actually costs some overhead. Okay, so you are taxing every request by adding a request thread creation and a thread deletion overhead to the request processing overhead. Okay. In this case, this is a one shot. Right? You basically start it at the beginning. When the server starts up, you create this N thread, they live on till the server is terminated. Okay, one time overhead of creation that's amortized over the lifetime of the server. Okay, much better. Right? So this is why many servers will actually opt for the pre-spawned thread pool. Okay. Now, although I said that you statically create N, there are servers like Apache, for example, where that N is actually varied dynamically. Okay, so what you may do is, because I said if you have to pick N carefully based on the type of server you are running. Okay, that basically, as said, the system administrator has to somehow magically figure out the right N for every machine. Okay, it's not an easy task. It's going to be non-trivial to figure out. So the server can be smart about it. The server can say, I will start with a small N. Okay? Because you don't know the workload either. You may say that the server can handle 153 threads, but if there are no more than 5 requests coming in, there are 148 threads sitting there doing nothing. Right? So the number of threads has to be actually adapted to also the workload. So what many servers do in the pre-spawned case is when they start up, they start with a small number of threads. The pre-spawned pool is small, let's say you say 10. Okay? And then you see what the workload is doing. Or if requests start coming in and all the 10 threads are actually in use and other requests are queued up, you increase the size of the pool on the fly. Say, let me create 10 more threads. So now the pre-spawned pool has gone to 20. Okay? And so on. So you can keep expanding, and likewise if you see lots of threads idling, okay, I have 50 threads and only 20 are in use in the past 2 hours and these other 30 are just idling there, you can start shrinking the pre-spawn pool. Yeah, so this pool can grow and shrink. Okay. You can even set caps on the maximum size to which this pool can grow to. Okay. That would be your limit of N. Saying the system administrator can say N should never be more than 300 for this machine. Okay. And then the server will just obey it. It will vary from 10 to 300 but never exceed 300. Okay. Or the system can figure that out. Okay. As you keep growing, if you just start seeing that there are lots of page faults, or CPU is always at 95% utilization, the server can say, looks like it's maxed out, let me not increase the thread pool beyond this point, even if requests come in. So that can also be automated. So in other words, your pre-spawned pool can be made more dynamic like the thread per request, but except that each thread lives on to service more than one request, and thus the thread creation, deletion, overheads are amortized for multiple requests. Okay. That server design, iterative concurrent, something to think about. If you design your server outside of your lab, what are you going to pick? Okay. Is it iterative, is concurrent, is it thread per request, pre-spawned pool, all design choices. Okay. The next set of issues are sort of more trivial here. This is basically saying that how does the client know where the server is? If the client has to communicate with the server, it needs to know the IP address of the server, okay, and or the name of the server, okay, www or something.foo.com. and it needs to know the endpoint, which is the socket port number that the server is listening on. Typically, to enable communication, you need to know these two things. Okay, what is the port that the server is listening on? What's the address of the server? Simplest approach is hard code it in the client. Okay, the client is reconfigured to say server is always going to be at 128, 119 something or something. Is always going to listen at port whatever 1500. Okay. You can hard code this in the client, and when the client starts up, it always makes a connection to that IP address, that port number, and you are done. Okay. Now this is very simple because the client doesn't have to figure out where the server lives. Okay. But it is restrictive from the server end because whoever is deploying the server has to hard code that in the client. You can't move it once you deploy the client. If you move the server to another IP address, things don't work anymore. So the clients are still connecting to the hard coded address. Okay. So what would you do? Yes.
And click on mapping in the third-party server, and so you just get the server name, and the server name can translate to the database and
So if you, so the very straightforward approach is if you don't know, ask someone. Okay? If you don't know where the server is, ask someone where the server is. Okay? So this is typically done using what is called a directory service. Okay? What a directory service is simply a table, exactly what was mentioned. Okay, whenever servers come up, when they start up, they register themselves with the directory service, saying, I am a printer, print server. Okay? If some machine needs to find a print, you say, I am a print server, this is my IP address. You register. Okay, the directory service just has a table saying, these are all the servers that have registered with me, these are their IP address, these are their port numbers. So when the client comes up, it simply asks the directory service, saying, where is a server of this type? Where is a print server? Okay? Where is this other server that provides this kind of service? And the directory service is at this IP address and this port number. So you get that, then you can basically establish a connection to the server. Okay? So hard coding is one approach. Using a directory service is another approach. Typically, most systems will use a directory service. That way, you can move the server on any other machine, and when it comes up, it just registers itself with this new identity, and clients will just continue to work fine. They'll just make a directory lookup and be redirected to the new location, for instance. Okay? So, directory service, there are many different ways to implement directory service. We'll come back to this later on. There's something called LDAP, Lightweight Directory Access Protocol. That's a directory service. If you use RPCs, there's a process called a port mapper in Unix. That's a directory service. There are many different kinds. There is something called Yellow Pages, which is not your phone book Yellow Pages. It's a process that runs. That's also a directory service. Many different kinds of directory services. Okay. So you could use a directory service, but if you're paying attention, you could have asked a question, which is, how does the client know where the directory service is? Right, so you need to first find a directory service to ask the directory service. Directory service is another type of a server. Okay, how do you know where it resides? Yes, what do you say?
you can keep a list of the servers and try one by one, and if one of these servers is okay, and you can update the table.
Okay, so you give a list of all possible places you can run a directory service, and you just say, is it here, is it here, is it here? Right? That's one approach. Okay, it's not a bad approach. Second approach is you hard code the directory service. You say a directory service can be hard coded, okay, and you basically just go look it up. Okay. Two approaches. Any other approaches?
You broadcast from the directory.
Okay, you broadcast. You don't know the directory service. You start screaming, where are you, directory service? Essentially,
you should listen for the directory service to announce where it is.
okay, you could listen. So directory service is the one broadcasting its identity. You go and wait and listen for one, or you go and ask for one. Okay, both of those approaches are actually valid. In one case, the server is advertising its presence using a broadcast packet. I mean, literally this packet will go to every machine on your LAN. Okay, and then you just wait for a packet. Or you send a broadcast packet saying, is there a directory service? Okay, and you basically send a what's called a discovery packet that also goes to all machines. And if any of those machines actually has a direct service, it receives that packet and responds directly to the sender. Okay, so you can use broadcast either from the server side or the receiver side. One approach. You hard code, but you don't have to. The thing to keep in mind is you don't have to hard code the directory service into your client process. You can hard code this on the machine and a configuration file. Okay, typically, that's what is done. You can actually you have etc files in Linux. Because a directory service will be used by lots of different client server applications, so it's a system-wide service that you're providing. So the system administrator can actually hard code it onto a configuration file on that machine. The client just has to go look up that file and figure out where it is, rather than hard coding it in the client process itself. Okay? So hard code it in a configuration file, put it in a direct broadcast, or those are the only two approaches. Okay, the third approach was you have a list where you have pre-configured possible places and you go look. Okay, so those are approaches. So these are all issues that you will have to think about. Okay? So maybe when you do your client server, you use a directory service. If so, how? Or when you hard code the server address and not worry about it. So there will be different design choices with different implications. Okay. Second point is whether the server is going to be stateful or stateless. Okay. This may not make much sense at the moment, but when we come back to looking at consistency and caching and all these other ideas, we will see that it does matter whether the server keeps state or doesn't keep state. So what does state mean? So state can mean many different things. In this case, the state simply means the server actively have a table that keeps track of which clients are connected to it at the moment. That state of all the clients that are connected to the server, or the server just doesn't bother. Request comes in, you service the request. You forget what client it was and then wait for the next request. Okay? So if you keep track of which clients are connected to it, you are a stateful server. If you don't keep track of that, you are a stateless server. Okay? And so you may do multiple things. You can design your server to be stateless, or you can design the server to be stateful. Okay? Think of a bookstore. Okay? So when the client connects to an online bookstore, okay? The server might keep state of the client. Okay? In addition to the IP address, it may keep other state like the shopping cart. You put an item in the shopping cart, that state that the server has maintained for the session. You can even go back later and the shopping cart will still be there. Okay, that's a stateful server. Okay. You can design the server to be stateless, saying the server doesn't have to deal with all of this. Just if you need to keep track of something, you can do it on the client. Okay, so you can design your shopping cart to be a browser cookie that you send back to the browser, saying it's an encrypted cookie. It has the items in the shopping cart, you send it, so when the browser connects the next time, it presents that, so now you know what was in the shopping cart. Server doesn't have to track it. Okay, so you can keep any information you want at the client end, in which case the server design is simpler, it's stateless, or you can put more burden on the server, keep more track of more things at the server, client becomes simpler. Okay, so you have to make these design choices judiciously. Where do you want to keep more intelligence, more state? Okay, that will result in different design choices in the client server system. Okay. There's something also called a soft state. So what soft state essentially means is the server is keeping track of, is caching some state, but it's not going to keep what's called hard state. It's the correctness of the client server application is not impacted by whether that state exists or not. It's possible to throw it away and you will still be able to make it work. So think of it as a cache. Right? If you throw out the cache state, basically things take longer, but things still work. Just as if you have a cache miss, okay, you still get whatever you requested, but it takes longer to get. Okay, so some servers keep soft state, so that it's possible for them to discard that. So we'll come back to soft state also when we talk about consistency. Okay. So just a couple more slides here. So here is an example of a clustered server. So here we have these tiers of the servers where each tier is replicated. So when you have very large servers, not only do you split the functionality across multiple tiers, each tier is replicated on multiple machines. As is shown here, your database replicated on 3 different servers. You have your Java tier of your server replicated on 6 machines, and so on. So in this case, what happens is when the request comes in, okay, there has to be a dispatcher or a scheduler here which says which of these machines should handle that request. Just as in a multi-threaded server with a pre-spawned pool, when a request comes in, there's a dispatcher that says here is an idle thread, go service it. Same thing is true here. When request comes in, you have to pick a machine to that will service that request. So that's basically going to forward your incoming. So you have a dispatcher that says this request is going to be serviced by that machine, and then that machine does whatever it needs to do to service that request. Right? So there are these dispatchers are also called load balancers. Okay? The requests that are coming in are balanced. You do load balancing of these requests across your pool of servers. Okay? So you can have round robin, saying each successive request is assigned to successive server, so the load gets spread out, or you can have many different policies in the dispatcher. Okay? So the dispatcher has algorithms that tell it how to pick which machine will service a request. You can say least loaded. Okay? Of all the machines, you always keep track of the load. New request comes in, send it to the least loaded machine, and so on. Okay? Now that's what a typical dispatcher does, but in reality, the dispatcher has to do a lot more sophisticated things, because whenever you have these servers, typically the servers are stateful. They are keeping track of the state of the request. You can't simply just send a request to whichever server you want. The reason is, let's say user has established a session. Let's say this is some e-commerce site, Amazon or eBay or one such site. You come in and let's say you're browsing, and then as I said, let's go back to the shopping cart example. You take an item, you put it in the shopping cart. Okay, that state that the server is maintaining. Okay. Typically that state is going to be stored in the memory of one of these servers, wherever the request of service. The next request comes where you say go buy. If you just have that request come in and you send it to the least loaded server on some other machine in that pool, that server doesn't have the shopping cart state. That state was on another machine. Right? So you have to keep track of not only load on the machines, but you have to keep track of this notion of a user session. Okay? So if previous requests from this user session were sent to a server, server 10, subsequent requests should also be sent to that server, because that server may be keeping state of that session. If you simply send it to a new machine, that machine won't know what to do with that request. Okay? So you can load balance at the session level, not at the request level in many applications. Additional complication to deal with. Okay? Hopefully in this class you don't need to deal with sessions and things like that. Here is another example of what a dispatcher does. So I simply said request comes in, you just forward that request to whatever machine you want. Okay? So there are actually, you have to do things at the network level. What does it mean to forward and so on. Okay, the reason is the following. Okay, so here is your dispatcher. That's the pool of server that's sitting behind the dispatcher. When the client actually sends a request, typically this is a TCP request. To send a TCP request, you have to first set up a TCP connection. Okay, if you know anything about TCP, there's a 3-way handshake that you have to do to establish a TCP connection. So in some sense, the client has established a connection with the dispatcher, okay, and it sent the request to the dispatcher. Now this request here is being forwarded to this server. Okay. The connection actually has been established to the switch, not to that server. Okay, because if you send an HTTP request, okay, you send the HTTP request, this is acting as sort of the overall front end for your system. So the HTTP connection, which is essentially a TCP connection underneath HTTP, has been established to this machine. Okay. Now, if this machine says that server is responsible for servicing the request, you cannot simply just take that TCP connection and move that here. It is bound to this machine here, not to that machine. So how do you deal with that situation? There are multiple techniques you have to employ at the network level to deal with it. Simplest one is called TCP splicing. Right? What TCP splicing does is, if this switch decides that this server services that request, this switch sets up a separate TCP connection from here to here. Okay? And it simply splices these two connections. Splices essentially mean you just connect them to one another. So packets that come on this connection from here to here are simply copied to a new connection from here to here. Requests that flow back from the switch on this connection are simply sort of relayed back. You just copy. So you are just copying data from one TCP connection to another. Okay? This is called TCP splicing. Okay? Another mechanism is what is referred to as TCP handoff. Okay? TCP handoff, you are explicitly handing off your TCP request as is being shown here, even though the connection was actually established here, to hand off that connection there. Okay? You can do this at the TCP level or HTTP level. Okay? At HTTP level, you can just put an HTTP redirect. Okay? HTTP redirect will just redirect the HTTP connection to a new server. And from that point on, the client can directly communicate with the server. Okay? You can also do this at the TCP level, which is more complicated. I won't go into all of the details here, but that essentially switches the TCP connection. Okay? So many different aspects have to be dealt with when you have clustered architecture. How do you load balance? What algorithm to pick for load balancing? How do you handle session state? Okay, so you don't want to send a new request from that session to another server because the state may be on different server, keeping track of state. How do you make it work at the network level? Because what you are connecting to may not be the entity that's servicing. You connect to the switch, you are serviced by a server, and there are two different machines. Okay, how do you, when your connection has gone to one machine, how do you switch it? So all of these details have to be dealt with. We will come back to some of this later on in the course. Okay, today we have run out of time, so I'm going to just stop here. Okay, so just a reminder that we sent an email, there's a homework out due early next week. Okay. I think the next class is on Tuesday, okay, because Tuesday is Monday's schedule. We'll just keep that in mind.